Dear students, once again welcome to EduSat learning platform. In the previous episode, we were discussing about examples or applications of Kirchhoff's law. Basically, we have seen how dissimilar cells are connected in series and parallel, the effective EMF and the effective resistance of the circuit. Now, let us start with another example. Suppose there are two cells, 12 volt having internal resistance of suppose 3 ohm and another 6 volt having internal resistance of suppose 2 ohm, they are connected in parallel. Now, let us calculate. Suppose this is A, B, C, D and M, N. Let us calculate what is the potential difference between the 2 points M and N. To calculate this, suppose my current is I here. This is disconnected, so therefore, the current will flow in this circuit. So, my current is I here. Now, let us apply Kirchhoff's law here. Applying Kirchhoff's law, what we get? My I is equal to 12 minus 6 divided by 3 plus 2. So, it is 6 divided by 5, it is 1.2 ampere. So, current in this part of the network is 1.2 ampere. So, let us calculate the potential difference between A and B. So, if I start with A, VA, current is flowing in this direction. So, therefore, this cell is opposing me. So, it is minus 12 volt and my potential is lower than the potential of this resistor. So, therefore, it is plus 3 into 1.2 and then I come to B. So, VAB will be equal to, it is 12 minus 3.6 volt. So, this is 8.4 volt. Now, let us calculate the potential difference between C and D. So, VC again 6 volt is opposing me. So, it is minus 6 volt, but I am in this direction. So, my potential is higher than this resistor, potential across the resistor. So, it is minus 2 into 1.2 volt equal to VB. So, VCD equal to 6 plus 2.4, it is 8.4 volt. So, therefore, what is VAB? The same as VCD and this is VMN. So, VMN is also equal to 8.4 volt. Now, let us calculate the same thing by using the formula. What is the effective EMF or E equivalent? E equivalent is E1 R2 plus E2 R1 divided by R1 plus R2. Let us check it out whether it is correct or not. So, it is 12 into 2, 24 plus 6 into 3, 18 divided by 3 plus 2 is 5. So, it is coming like 442 divided by 5, it is 8.4 volt. Okay. This formula we have calculated by using the same principle, Kirchhoff's law. So, if let us see that this 6 volt is reversely connected. If this is suppose reversely connected, then what will happen? If this is reversely connected, this is 12 plus 6 and this will be 18 divided by 5 and this is 3.6 ampere. Now, my VA will be equal to VA minus 12 volt plus 3 into 3.6 equal to VB. So, it is this will be VAB will be, it is 12 minus 10.8. This is simply 1.2 volt. If this 6 volt is just altered, then similarly in this case also we are getting 2 into 3.6 and this is 6.6. So, this will be if this is altered, then this is plus 6 volt and minus this one. So, VCD will be 6 minus 7.2 and this is 1.2 volt. Okay. So, again VAB VCD equal to VMN. So, here we have to consider the another formula U1 R2 minus E2 R1, because E2 is reversely connected. So, it is minus. So, minus E2 R1 by R1 plus R2. So, it is 24 minus 18 divided by 5, it is 6 by 5 and this is coming as 1.2 volt. You see, in any way, if you are clear about the concepts and clear about the application of Kirchhoff's law, then you will get the same thing in whichever way you are working. Now, let us consider another small network, a linear network. Suppose in a linear network of resistor and cells, what is the potential difference? Suppose I have a combination of this is my point A and this is my point B, and this is suppose 10 volt, this is 5 volt and this is 7 volt. This is 1 ohm, 2 ohm, 1 ohm and this is 1 ohm. And if my current is 2 ampere, current of 2 ampere is flowing in this linear chain of resistors and cells, then what is the potential difference between A and B? Starting with A, this is my potential VA. When I proceed, I get a passive element. Passive element always drops your potential. So, my potential will be dropped by 2 into 1 IR. So, it is 2 volt. When I proceed further, what I see that a battery is connected reversely. So, it will drop my potential again minus 10 volt. Now, proceeding further, again this resistor will drop my potential again 4 volt, and this battery supports me, gives me potential plus 5 volt, and this is minus 2 volt, minus 7 volt, minus again 2 volt, and finally, I arrive at B. So, VA minus VB, or we can say VAB, this will be equal to all the negatives will be positive, 7 plus 2 9 to 11, 11 4 15 25 to 27 volt minus 5 volt. This is 22 volt. So, the potential difference between A and B is 22 volt, and similarly we can also calculate if there are some capacitors in between, that will not be a problem. Okay. So, in this way, by using Kirchhoff's law, we can find the potential difference across a network, the potential difference between 2 points in a network. Okay. Now, let us see how we can use Kirchhoff's law to find the balanced condition of a Wheatstone's bridge. A Wheatstone's bridge is a network of resistors there are 5 resistors connected in such a way that they form a bridge. Suppose the resistances are P, Q, R and S, and there is another resistance X. So, this is a Wheatstone's bridge. Okay. Now, let us calculate the balanced condition. Let us find the balanced condition of this bridge. The meaning of balanced condition is, if this is A, B, C and D, the balanced condition means VB equal to VD implies as VVD equal to 0, means there will be no current through this branch X of this Wheatstone's bridge. So, to find this one, let us connect these two ends to a battery and let a current I is entering into the bridge. If the branch P has a current of I 1, then this will be obviously I minus I 1 by using the Kirchhoff's first law or the junction law. And similarly, let this is I 2 and this will be obviously I 1 minus I 2. So, this will be I minus I 1 plus I 2 and this is equal to I. So, the amount of current entering to the network or Wheatstone's bridge is equal to the amount of current outgoing from the bridge, means it is according to Kirchhoff's first law we have applied successfully. Okay. Now, to find out the value of I 2, which is 0 in case of balanced condition, now let us apply Kirchhoff's second law to these two networks. In the first network, what I get? 0 equal to means there is no EMF. So, since there is no EMF present inside the two networks, two meshes, therefore, the EMF is 0. So, equal to I 1 P plus I 2 X minus I minus I 1 into R. And similarly, in the second mesh, what I get? 0 equal to I 1 minus I 2 Q minus I minus I 1 plus I 2 S minus I 2 X. This is my equation number 1 and this is my equation number 2. Now, if the bridge is balanced, then I 2 is equal to 0, because VB equal to VD or VBD equal to 0. So, I 2 equal to 0, this implies in equation 1 I get I 1 P is equal to I minus I 1 into R, and from equation 2 I get I 1 Q is equal to I minus I 1 into S, putting I 2 equal to 0. So, this is my equation number 3 and equation number 4. Now, dividing equation 3 and 4, what I get is P by Q equal to R by S, or P by R equal to Q by S. Now, let us notice what is the meaning of this one. If P by Q equal to R by S or P by R equal to Q by S, in either way we are getting the bridge is balanced and there is no current passing through this resistor, or we can say this resistor is useless for this circuit. Okay. Now, this balanced condition of Wheatstone's bridge is mainly used to find the effective resistance of a complicated network in which a bridge is there. So, to start with a practical problem, suppose we have a network like this, this is 1 ohm, 1 ohm, 1 ohm, 1 ohm, and this is also 1 ohm. So, if it is asked to find out what is the effective resistance between A and B, because this resistance central resistance 1 ohm, diagonal resistance 1 ohm, it is connected in such a way that we cannot say the whether it what are the resistances in series, what are in parallel. So, therefore, what we get here that this bridge is balanced. This is a Wheatstone's bridge and bridge is balanced where 1 by 1 equal to 1 by 1. So, this indicates that this 1 ohm resistor will be useless for the circuit. So, the equivalent circuit will be like this: A B, this is 1 ohm, 1 ohm, 1 ohm, 1 ohm. So, the effective resistance are equal to 1 plus 1 2, 1 plus 1 2, 2 and 2 are in parallel. So, the effective resistance is 1 ohm. So, in this way we can use the balanced condition of Wheatstone's bridge to find out the effective resistance. So, now let us start with some more examples of balanced condition of Wheatstone's bridge. Suppose I have another network like consisting of, suppose a network is like this, where each resistance is 1 ohm. Now, to find out the effective resistance between A and B. To find the effective resistance, what we see, the upper part of this diagram is a balanced Wheatstone's bridge, where this resistance is becoming useless for the circuit. So, therefore, the equivalent figure is becoming equal to like this. So, this is 1, 1, 1, 1 and 1. So, 2 and 2 in parallel. So, it is 2, 2 and 1. So, effective resistance R will be 1 by R will be equal to 1 plus 1 by 2 plus 1 by 2. So, this is 2 plus 2 4, 4 by 2. So, it is R equal to half. So, this is the effective resistance of this network. So, now let us calculate the effective resistance when the bridge is not balanced. When a bridge is not balanced, let us calculate the effective resistance. Suppose this is 1 ohm, this is 1 ohm, this is 2 ohm, this is 1 ohm and this is 1 ohm. Now, in this case what we see that P by Q is not equal to R by S, P by Q is not equal to R by S, implies bridge is not balanced. So, in this case we have to follow the first principle to find out the effective resistance between A and B. Suppose A and B are connected to a battery. What will happen then? If suppose unit current is entering into the junction and this is X. So, this is 1 minus X my current and this is Y. So, this will be X minus Y and this will be 1 minus X plus Y and this is 1. So, unit current is entering into the junction and unit current is going away from the junction, coming out of the network. So, now let us apply Kirchhoff's law in both the meshes. In the first mesh I get X. What is my intention? My intention is to find out the values of X and Y, so that I can get the potential difference between A and B or the effective resistance between A and B. So, 1 into X plus 1 into Y minus 1 minus X into 1 equal to 0. So, this implies as 2X plus Y equal to 1. This is my equation number 1. 2X plus Y equal to 1. So, this is my equation number 1. Similarly, in the second mesh, I get X minus Y into 1 minus 2 into 1 minus X plus Y minus Y equal to 0. So, I get so 3x 2x x 3x minus 2y minus y minus 3y 3x minus 3y 3x minus 3y minus y. So, 4y equal to 2. This is my equation number 2. So, 3x minus 4y equal to 2. This is my equation number 2. Now, multiplying 4 in equation 1, you will get 8x plus 4y equal to 4. This is my equation number 3. Now, adding 2 and 3, you will get 11x equal to 6 or x equal to 6 by 11. If x equal to 6 by 11, what is x? X is the current flowing through this branch of the Wheatstone's bridge, unbalanced Wheatstone's bridge. So, if x equal to 6 by 11, then what is y? Y is 1 minus 2x, y is 1 minus 2x, it is 1 minus 2x is 12 by 11. So, it is minus 1 by 11. So, y is 1 minus 2x. So, it is minus 1 by 11. The negative sign indicates that the direction in which we have taken the current y is actually reversed, because the current is actually flowing in opposite direction. So, therefore, we are getting a negative sign, nothing more. So, now knowing the value of x minus y or x and y, now let us try to find out between the potential difference between A and B and also the effective resistance. So, if I start with A, so what I get is this is A B, suppose this is my C or this is my D. In whichever path you want to go, you can move. Suppose I move from A to B through C. So, VAB equal to VAC plus VCB. What is VAB? VAB is the potential difference across the entire bridge. So, this is equal to current through the bridge 1 into the effective resistance between AB. VAC is current into resistance, current is X into resistance is 1 ohm, plus V C B is current is X minus Y and the resistance is 1 ohm. So, this will give me 6 by 11 plus X minus Y is 7 by 11, 7 by 11 ohm. So, this will give me R A B equal to 13 by 11 ohm. So, this is the effective resistance between the points A B. Now, let us calculate the same effective resistance while going through the other side. V A B equal to V A D plus V D B. So, this is 1 into R A B equal to 1 minus x into 1 plus 1 minus x plus y into 2. If you calculate, R A B will be again come as 13 by 11 ohm. So, in this way, if the bridge is not balanced, we can find out the effective resistance in a circuit. We have already seen to calculate the effective resistance of complicated networks in case of balanced bridge, Wheatstone's bridge, and also in case of unbalanced Wheatstone's bridge by applying Kirchhoff's law. Now, let us see some more examples. Suppose there are 12 resistors connected on the sides of a cube. Like this. And we have to find out the effective resistance between the points A and B. This can be done by using Kirchhoff's first law. Suppose one is the amount of current entering into this network. So, it will be equally divided. So, it is 1 by 3, 1 by 3 and 1 by 3. Again 1 by 3 will be divided into 1 by 6 and 1 by 6, and here it is 1 by 6, 1 by 6. Again they will reunite to give you 1/3 of total current, 1/3 of total current and 1/3 of total current. So, 1 unit of current is going out of the network. So, therefore, what we see is if I go from A to B, suppose this is A C D B. So, V A C D B is V A C plus V C D plus V D B. So, R into 1 equal to, and if all the resistances are R, then it is 1/3 of R plus 1/6 of R plus 1/3 of R. So, this is 5 by 6 R. So, my effective resistance between the points A and B will be 5 by 6 R, where R is the resistance on any branch of this network. Now, let us find the solutions for some capacitive circuits. Now, let us consider a capacitive circuit like this. Suppose there are two capacitors, 2 microfarad and 4 microfarad, and there are 2 batteries. This is suppose 24 volt and this is 12 volt. Suppose this point is A and this point is B. Find the potential difference V A B, the potential difference between the points A and B. So, to solve this one, this plate will be positive. So, this is plus Q, this is minus Q, and obviously, this will be plus Q and this will be minus Q. So, what we see here, that the positive plate of a capacitor is connected to the negative plate of another capacitor. So, obviously, we say they are in series. So, using Kirchhoff's law in this network, we get summation E equal to summation Q by C. In case of resistors, it was summation IR. In case of capacitors, it is summation Q by C, because Q equal to CV. So, what we get is here 24 minus 12 equal to 24 minus 12 is equal to summation Q by C. It is Q divided by 2 plus Q divided by 4. So, 12 equal to 3Q divided by 4. So, Q equal to 16 microcoulomb. So, the charge on the capacitors will be 16 microcoulomb each. So, therefore, if I calculate VA, if I come from VA, then it is minus Q by C. Q is 16 microcoulomb divided by 2 microfarad, and we come up at V. So, my VAB will be equal to 8 volt. So, the potential difference between the points A and B is 8 volt. So, in this way, by using Kirchhoff's law, we can find out the potential difference between any 2 points. Similarly, we can also calculate the effective capacitance between 2 points in a network. To find the effective capacitance between 2 points, now let us consider a similar situation of unbalanced Wheatstone's bridge. This is an unbalanced Wheatstone's bridge where the capacitors are connected like this. This is suppose 1 microfarad, 1 microfarad, 1 microfarad, this is 2 microfarad, and this is 1 microfarad. Okay. This bridge is also unbalanced. This is a Wheatstone's bridge of capacitors, and this is also unbalanced. Now, if I consider that unit charge is entering to the network, and if Q is the amount of charge developed here, so this is 1 minus Q on this plate. So, this is plus, this is minus. So, suppose this is plus Q1. So, this will be, this is minus Q. So, this is plus Q minus Q1 on this capacitor, plus minus. So, this is minus Q1, this is minus of 1 minus Q. So, this is plus of 1 minus Q plus Q1. So, this is minus of 1 minus Q minus Q1. Now, minus of 1 minus Q. So, this is minus of Q minus Q1. So, minus Q plus Q 0 plus Q1 minus Q1 0. So, this is minus 1. So, in this fashion we can develop charges just like summation I equal to 0, summation Q equal to 0 at any junction. So, now we can apply Kirchhoff's law to the networks. And in the first network, if I use Kirchhoff's law, it is 0 equal to Q divided by 1 plus Q1 divided by 1 minus 1 minus Q divided by 1 equal to 0. So, this will give me, this is 2Q plus Q1 equal to 1. This is my equation number 1. And similarly, from the second one, I get 0 equal to Q minus Q1 by 1 minus 1 minus Q minus Q1, 1 minus Q plus Q1 divided by 2 minus Q1 by 1 equal to 0. So, from this we will get, it is 2Q plus Q 3Q. So, it is 3Q, this is minus 2Q1 minus Q1 minus 2Q1. So, minus 5 q1 equal to 1 equal to 1. This is my equation number 2. Now, to solve these two, now let us solve these two to find out the values of q and q1. So, if I multiply 5 here, so 10 q plus 5 q1, 10 q plus 5 q1 equal to 5, equation number 3. So, now solving this, you will get 13 q equal to 6. So, q equal to 6 by 13, and similarly the value of q1 is 1 minus 2 q. So, it is 1 by 13, 1 minus 2 q is 1 by 13. So, knowing the values of q and q1, now we can find out, suppose this is A, this is B and this is C. So, V AC equal to V AB plus V BC. So, V AC is how much? It is Q by C AC equal to, total charge is 1, total capacity, let it is CAC, effective capacitance. So, VAB is, total charge is Q, it is 6 by 13 divided by capacity is 1, plus VBC, it is Q minus Q1, Q minus Q1 is 5 by 13 divided by 1. So, this is equal to 11 by 13. So, C, the effective capacitance between A and C is 13 by 11 microfarad. So, in this way, using Kirchhoff's first law and second law, we can also calculate the effective capacitance in a complicated network where the bridge is not balanced. Okay. So, this is something about the applications of Kirchhoff's law, some examples showing the applications of Kirchhoff's law. Now, let us see another instrument which is helping us a lot to find the exact potential difference between 2 points. In all these circuits, we have seen that the potential difference between 2 points can be calculated by considering EMFs present, by considering current, by considering resistance. But the instruments like ammeter, voltmeter, they are used to measure the current in an electrical network and voltage in an electrical network. In an ammeter, what we use? We use a very small resistance in series, and in voltmeter, we use a very high resistance in parallel. What is the concept? The concept is, we have to connect a voltmeter. Suppose I have a battery, there is a resistance, this is ER, there is a resistance, and now I connect a voltmeter across this resistance. If I is the current flowing, if this voltmeter is ideal, then the current flowing through the voltmeter I dash will be equal to 0. To get I dash equal to 0, or if I have I dash equal to 0, then the entire current will pass through the resistance R. So, my V will be equal to IR. So, it can be written as E minus IR also, where R is the internal resistance. But to get I dash equal to 0, we have to make the resistance of this voltmeter very high, or we can say infinite resistance, which is not within our control. We cannot make the resistance of a voltmeter to infinity. This is a very absurd thing. So, therefore, it is impossible to measure the potential between 2 points in a network by using exact potential by using a voltmeter. So, here comes the concept of an ideal voltmeter, which is having infinite resistance, which is not at all possible. To calculate the exact potential difference between 2 points, we develop another instrument known as potentiometer. What a potentiometer is? Now, let us see. Basically, a potentiometer is a bridge, Wheatstone's bridge, having a wire of calibration, a long wire of calibration. Suppose these are 2 points where I have connected a wire of length 1 meter. Now, suppose I have 2 gaps and here there is a biasing voltage E. E is the biasing voltage to the network. Now, from the middle point, I have connected a galvanometer with a jockey. Let there is an unknown resistance connected across this gap and a known resistance of suppose R across this gap. Now, if the jockey is slided over this wire, since the wire is of a length 1 meter, this is a Wheatstone's bridge, basically a Wheatstone's bridge PQRS. So, if the wire is of length 1 meter, then it is known as a meter bridge. If I slide the jockey, then at some point, suppose L from left and therefore 100 minus L or in centimeter from right, the current through the galvanometer is suppose 0. So, this indicates that x by L P by Q equal to R by S, 100 minus L, since the wire is of uniform resistivity. So, the value of x can be calculated as R into L divided by 100 minus L. This is the way in which we use the meter bridge, a meter bridge which is actually the application of Wheatstone's bridge to find the unknown resistance, If I change the length of this meter bridge wire to any length like 10 meter, 20 meter, 30 meter, then actually it becomes a potentiometer. In this case, what is the merit of a potentiometer over a voltmeter is? There is no current through the galvanometer, means there is no transfer of current from one branch of the network to the other branch, unlike the voltmeter. In voltmeter, some current passes through voltmeter and therefore, the exact value of potential differential V cannot be calculated by using the voltmeter, which is not happening in case of a potentiometer. We will see potentiometer after a while. The figure drawn in the whiteboard is actually a meter bridge. The length of the wire is 1 meter, therefore, it is known as a meter bridge. And we have seen how we can calculate the value of an unknown resistance by using a meter bridge. If we change the wire of this meter bridge, which is taken as 1 meter, if we take it as suppose 10 meter, if we take the wire, the length of the wire as 10 meter, we can increase the length like this. If I take it as a suppose 10 meter long wire, then what will happen, that the same potential is now be dropped, potential E is now dropped across a length of 10 meter. So, therefore, the potential per meter will be E divided by 10, which was initially E by 1. In this way, we can calibrate the potentiometer to calculate a very small potential difference across a network. The potentiometer can be effectively used to find the EMF of a battery, the internal resistance of a battery, or it can also be used to find out or to compare the EMF of two cells. Now, let us see how a potentiometer is calculated. Potentiometer is used to calculate the EMF of a battery. Suppose this is my potentiometer wire and it is biased and like this. Now, another battery is used. Battery of EMF E dash, and here is my galvanometer and this is my jockey. Let at a length L, the current through the galvanometer I is becoming equal to 0. This wire between A and B, it is the potentiometer wire of a desired length. We can take a higher length to lower the least count of this potentiometer, to measure smaller and smaller voltage by using the potentiometer. Now, if the galvanometer shows 0 deflection, the current through this branch is becoming 0 at this point, it means that the potential across the length L of this wire is equal to the EMF E dash. So, therefore, if this is my E and capital L is the length of the potentiometer wire, then potential per unit length, or we can say the specific potential is equal to E by L. So, therefore, V equal to the V across this point, this small length L is E by L into small l. This is my V, and which is equal to E dash. So, that there is no current passing through the galvanometer and it is balanced. So, this implies is the EMF of the cell E dash equal to E into L divided by capital L, where E is the biasing voltage across the potentiometer, L is the length at which the bridge is balanced or current is 0 through the galvanometer, and capital L is the total length of the potentiometer wire. Okay. Similarly, by using another battery, we can compare the EMF of two cells by using the potentiometer. How? Let us see. Suppose there are two batteries E1 and another battery is E2. Here there is key K1 and this is key K2. Now, suppose the battery E1 is balancing at a length L1. When K2 is open, K1 is closed, the balance point is suppose at L1. Similarly, when K1 is closed, K2 is closed and K1 is open, suppose E2 is balanced at L2. So, we can write E1 equal to L1 E divided by capital L and E2 equal to L2 E divided by capital L. So, therefore, E1 divided by E2 will be equal to L1 divided by L2. So, in this way knowing the values of L1 and L2, we can find out the value of or the ratio between E1 and E2, the relation between the EMF of two cells. This potentiometer can also be used to find the internal resistance of a battery. To find the internal resistance, suppose we have a battery of EMF E, battery of EMF E having internal resistance, and there is a load R across this battery E dash and internal resistance R, like this. Now, this is the necessary circuit. Suppose this K is open. If this K is open, this key is open, then it is suppose balancing at a length L1. If it is balancing at a length L1, then obviously we are having your E dash equal to E L divided by capital L. This is my formula. Now, suppose K is closed. If K is closed, there will be a current passing through this branch. What is the current I? The current I will be E dash divided by R plus R. The current I will be E dash divided by R plus R. Let us take this point as A and this point as B. When this battery is open, then the potential difference between A and B is E dash, and it is suppose balancing with L section of this wire. So, my E dash will be equal to E L divided by capital L. Now, if when K is closed, then there will be a current flowing through this network, and the current will be I equal to E dash by R plus R. So, V A B equal to E dash R divided by R plus R, because V A B equal to I R. This is E dash R divided by R plus R. Now, let V A B is balancing with L dash section of this wire. If it is balancing with L dash section of this wire, so this will be equal to L dash section of this wire. So, that will be equal to E L dash divided by L. Now, this was my equation number 1 and this is my equation number 2. Now, dividing these two, we will get R divided by R plus R is equal to R divided by R plus R is equal to L dash divided by L. L dash divided by L. So, R L plus R L dash, sorry, R L equal to R L dash plus small r L dash. So, now this implies R equal to R into L minus L dash divided by L dash. So, in this way we can find out the internal resistance of a battery by connecting another resistance R in parallel. R is known, L is known, L dash is known. So, we can calculate the value of internal resistance. So, in this way we have seen the potentiometer has 3 type of application. It can be used to find the accurate potential between 2 points of a circuit, number 1. Number 2, it can be used to find out the EMF of a battery. It can be used to compare the EMF of several batteries, and also it can be used to find the internal resistance of a battery. Thank you.